A very good afternoon friends, and in this video we are going to learn about the differentiation. Differentiation, as its definition I have already written on the board. It goes like this: a function fx. This is a real valued function. Real valued functions are the function which takes in the real number and gives out the real number. So a real valued function fx is said to be derivable or differentiable at x equals c if limit x tends to c fx minus fc over x minus c exists finitely. Now this value of this limit is called the differential coefficient of the function, and it is also written as f dash x or d by dx of fx. Now if you just look at this properly, this is just a limit, and you know that a limit said to exist finitely if the left hand limit and the right hand limit both exist. So now if I think about the left hand limit, so I write left hand derivative because it is going to give me a differential coefficient. So that's why I have written it as LHD. Now it goes like this. To make it simpler, I would like to convert this x tends to c as h tends to 0. And how to do that? So first, in the case of left hand limit, first let me write the basic. This is c minus, means the value of x will always be lesser than the c. Fx minus fc over x minus c. If I want to write this as h tends to 0, then the better suggestion goes like this. You just write here limit h tends to 0, and at the place of x you write c minus. So we make limit h tends to 0 at the place of x tends to c, and there you write f c minus h minus fc over c minus h minus c. Means what we are doing, that we are writing x as c minus h. So x is c minus h, and then when x tends to c minus, since x tends to c minus, then the h will be here. If you see, if I take h on this side, so I'll get h equal to c minus x. So h tends to c minus, and if x goes to c minus, means very close to c but still little lesser than c, so that it's almost close, therefore we write h tends to 0. So the limit x tends to c minus will be replaced by limit h tends to 0, and the x will be replaced by c minus h. So now see, if I further simplify, then this becomes limit h tends to 0, and this is f c minus h minus fc over minus h. So I hope you can see properly. Then I go for right hand differentiation. This I write here as RHD, and this one is limit h tends to c plus fx minus fc over x minus c. Again, in this case, we will change this x as c plus h. So we'll write x equal to c plus h, and when this h will be x minus c. So if h tends to c plus, means little over c, so this value, this x tends to h plus, then little over h, then this h is almost close to 0. So we will replace this fx by c plus h. So this becomes c plus h minus fc over x is c plus h minus c and this is limit h tends to 0. Now when every time we have limit h tends to 0 without minus or plus, then we will be in the better position to find the answer. So here also we have seen this one is limit h tends to 0, and here also this is limit h tends to 0. This is proper substitution so that we to avoid the confusion. Minus fc over c and c cancel, so this is h. So this is your right hand derivative, and if these two values are equal, then the function said to exist. Now if I change the definition, suppose if I want my function to exist at x equal to c, and the function is, this looks like the function is defined for the whole real number. Now if I say that my function is defined for in a closed or open interval, suppose if I take the c belongs to interval a comma b, means I have taken a, b, this is a is not included because this is open interval, so it means x is more than a and less than b. So it means a is little like this goes because b is not included, and then here I shade it like that. So this is whole real number. Now if I want the function to be differentiable in this open interval a comma b, then suppose c is in between, so it means between each and every point within this open interval, this function, this definition should hold true, where c can be here and here. But and every time we have to check the left hand limit and right hand limit for each and every point. But just look at this a point at this end a. Here you cannot change the, here you cannot take the left hand limit because there is no value before on this side, there is no value. Here you cannot take the right hand limit because there is no value. Then here we will only take the left hand limit. So just let me clear the mess, and I am just coming back to you again.
Zoom.
Okay, so the for function fx to be differentiable in the open interval ab, we need to find the right hand differentiation for this a, and it goes like limit x tends to a plus, because you cannot take a minus because there is no value before this a, because it is just after a, so we can take only RHS or the right hand limit. So limit x tends to a plus, and this will become f a minus, or I can better write this simply fx minus fa to be in sync with this, and x minus a. And for b you can write, so this one can be called as f dash a because we are taking at that point, and here you can find f dash b. So limit x tends to b minus fx minus fb over x minus b. So here, like at C, you have to find both left hand limit and right hand limit, but at these two extremes, here only you have to find right hand limit, and here only you have to find left hand limit, because it is not possible to find right hand limit in this case and the left hand limit in this case, because the point is defined just like this. X is greater than, so before a you can't find, and after b also you can't find. So this definition goes like this, and this is how you have to test whether you want to check the differentiability or the derivability of a function in open interval or closed interval in both cases, because you have to just go by the definition of the intervals, and in that interval at each and every point within that interval and at the end points also you have to check the differentiability, and then only you can find the answer. Thank you very much, and in the next video we will discuss more about how to find the relation between the continuity and the differentiability. Thank you very much. Have a nice time.